The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, because our subject today is trig integrals and substitutions, Professor Jerison called in his substitute teacher for today. That's me. Professor Miller. And I'm going to try to tell you about trig substitutions and trig integrals, and I'll be here tomorrow to do more of the same as well. So this is about trigonometry, and maybe the first thing I'll do is remind you of some basic things about trigonometry. So if I have a circle, all trigonometry is all based on this circle of radius 1 and centered at the origin. And so if this is an angle of theta up from the x-axis, then the coordinates of this point are cosine theta and sine theta. And so that leads right away to some trig identities, which you know very well, but I'm going to put them up here because we'll use them over and over again today. Remember the convention, sine squared of theta secretly means sine of theta quantity squared. It would be more sensible to write a parenthesis around the sine of theta and then say you square that. But everybody in the world puts the 2 up there over the sine, and so I'll do that too. So that follows just because the circle has radius 1, but then there are some other identities too, which I think you remember. I'll write them down here. Cosine of 2 theta, there's this double angle formula that says cosine of 2 theta is cosine squared of theta minus the sine squared of theta. And there's also the double angle formula for the sine of 2 theta. Remember what that says? 2 sine theta cosine theta. Now, I'm going to use these trig identities, and I'm going to use them in a slightly different way, and so I'd like to pay a little more attention to this one and get a different way of writing this one out. So this is actually the half angle formula. And that says I'm going to try to express the cosine of theta in terms of the cosine of 2 theta. So if I know the cosine of 2 theta, I want to try to express the cosine of theta in terms of it. Yeah, well, I'll start with the cosine of 2 theta and play with that. Okay, well, we know what this is. It's cosine squared theta minus the sine squared of theta. But we also know what the sine squared of theta is in terms of the cosine. So I can eliminate the sine squared from this picture. So this is equal to the cosine squared of theta minus the quantity 1 minus cosine squared of theta. I put in what sine squared is in terms of cosine squared. And so that's twice the cosine squared of theta minus 1. There's this cosine squared, which gets a plus sign because of these 2 minus signs. And there's the one that was there before, so altogether there are 2 of them. I want to isolate what cosine is, or rather what cosine squared is. So let's solve for that. So I'll put the 1 on the other side, and I get 1 plus cosine of 2 theta. And then I want to divide by this 2, and so that puts a 2 in this denominator here. So some people call that the half angle formula. It's a way of, what it really is for us is it's a way of eliminating powers from sines and cosines. I've gotten rid of this square at the expense of putting in a 2 theta here. We'll use that. And similarly, same calculation shows that the sine squared of theta is 1 minus cosine of 2 theta divided by 2. Same cosine, in that formula also, but it has a minus sign for the sine squared. Okay, so that's my little review of trig identities that we'll make use of as this lecture goes on. I want to talk about trig integrals, and you know some trig integrals, I'm sure, already. Well, let me write the differential form first. You know that d sine theta, or maybe I'll say d sine x, is, let's see, that's the derivative of sine x times dx, right? The derivative of sine x is cosine of x dx. And so if I integrate both sides here, the integral form of this is the integral of the cosine of x dx is the sine of x plus a constant. And the same way, d cosine of x is minus the sine of x dx, right? The derivative of the cosine is minus the sine. And when I integrate that, I find the integral of the sine of x dx is minus the cosine of x plus c. So that's our starting point. And the game today, for the first half of the lecture, is to use those basic integration formulas together with clever use of trig identities in order to compute more complicated formulas involving trig functions. So the first topic is to think about integrals of the form sine to the nth power of x, cosine to the nth power of x dx, where here I have in mind m and n are non-negative integers. So let's try to integrate these. I'll show you some applications of these pretty soon. Looking down the road a little bit, integrals like this show up in Fourier series and many other subjects in mathematics. It turns out they're quite important to be able to do, so that's why we're doing them now. Well, so there are two cases to think about here when you're integrating things like this. There's the easy case, and let's do that one first. The easy case is when at least one exponent is odd. That's the easy case. So, for example, suppose that I wanted to integrate, well, let's take the case m equals 1. So I'm integrating sine to the nth power of x times the cosine of x dx. I'm taking, I could do that one. Let's see if that's what I want to take. Yeah. My confusion is that I meant to have this a different power. You were thinking that. So let's do this case when m is 1. So the integral I'm trying to do is any power of the sine times the cosine. Well, here's the trick. Use this formula up at the top there to see cosine of x dx as something that we already have on the blackboard. So the way to exploit that is to make a substitution. And the substitution is going to be u is the sine of x. And here's why. Then this integral that I'm trying to do is the integral of u to the n. That's already a simplification. And then there's that cosine of x times dx. When you make a substitution, you've got to go all the way and replace everything in the expression by things involving this new variable that I've introduced. So I'd better get rid of the cosine of x dx and rewrite it in terms of du, or in terms of u, and I can do that because du, according to that formula, is the cosine of x dx. Let me put a box around that. That's our substitution when you make a substitution, you also want to compute the differential of the variable that you substitute in. So the cosine of x dx that appears here is just exactly du, and I've replaced this trig integral with something that doesn't involve trig functions at all. This is a lot easier. We can just plug into what we know here. This is u to the n plus 1 over n plus 1 plus a constant, and I've done the integral. But I'm not quite done with the problem yet, because to be nice to your reader and to yourself, you should go back at this point, probably go back and get rid of this new variable that you introduced. You're the one who introduced this variable u. Nobody except you really knows what it is, right? But the rest of the world knows what they asked for in the first place. That involved x. So I have to go back and get rid of this, and that's not hard to do in this case because u is the sine of x. And so I make this back substitution, and that's what you get. So there's the answer. Okay, so the game was I used this odd power of the cosine here, and I could see it appearing as the differential of the sine. So that's what made this substitution work. Let's do another example to see how that works out in a slightly different case. So here's another example. Okay, now I do have an odd power. One of the exponents is odd, so I'm in the easy case, but it's not 1. Okay, the game now is to use this trig identity to get rid of the largest even power that you can from this odd power here. So use sine squared of x is 1 minus the cosine squared of x to eliminate a lot of powers from that odd power. Watch what happens. So this is not really a substitution or anything. This is just a trig identity. This sine cubed is sine squared times the sine, and sine squared is 1 minus the cosine squared of x, and then I have the remaining sine of x, and then I have cosine squared of x dx. So let me rewrite that a little bit to see how this works out. This is the integral of cosine squared of x minus, and then there's the product of these two, that's cosine to the fourth of x, times the sine of x dx. So now I'm really exactly in the situation that I was in over here. I've got a single power of a sine or cosine. It happens that it's a sine here, but that's not going to cause any trouble. We can go ahead and play the same game that I did there. So far I've just been using trig identities, but now I'll use a trig substitution. And I think I want to write these as powers of a variable, and then this is going to be the differential of that variable. So I'll take u to be cosine of x, and that means that du is minus the sine of x dx. There's the substitution. And so when I make that substitution, what do we get? Cosine squared becomes u squared. Cosine to the fourth becomes u to the fourth. And sine of x dx becomes not quite du. Watch for the signum. Watch for this minus sign here. It becomes minus du. But that's OK. The minus sign comes outside, and I can integrate both of these powers. So I get minus u cubed over 3. And then this fourth power gives me a fifth power when I integrate. And don't forget the constant. Am I done? Not quite done. I have to back substitute and get rid of my choice of variable u and replace it with yours. Questions? There should indeed. I forgot this minus sign when I came down here, so these two gang up to give me a plus. Is that what the other question was about too? Thanks. So let's back substitute, and I'm going to put that over here. And the result is, well, I just replaced the u by cosine of x. So this is minus cosine cubed of x over 3 plus, thank you, cosine to the 5th of x over 5 plus a constant. And there's the answer. By the way, you can remember one of the nice things about doing an integral is it's fairly easy to check your answer. You can always differentiate the thing you get and see whether you get the right thing when you go back. It's not too hard to use the power rules and the differentiation rule for the cosine to get back to this if you want to check the work. Let's do one more example just to handle a case, an example of this easy case, which you might not have thought of it at first. Suppose I just want to integrate a cube, sine cubed of x. No cosine in sight. But I do have an odd power of a trig function, of a sine or cosine, so I'm in the easy case. And the procedure that I was suggesting says I want to take out the largest even power that I can from the sine cubed. So I'll take that out, that's a sine squared, and write it as 1 minus cosine squared. Well, now I'm very happy because it's just like the situation we had somewhere on the board here. It's just like the situation we had up here. I've got a power of a cosine times sine of x dx. So exactly the same substitution steps in. You get, and maybe you can see what happens without doing the work. Shall I do the work here? I'll make the same substitution. And so this is 1 minus u squared times minus du, which is u minus u cubed over 3. But then I want to put this minus sign in place, and so that gives me minus u plus u cubed over 3 plus a constant. And then I back substitute and get cosine of x plus cosine cubed of x over 3. So this is the easy case. If you have some odd power to play with, then you can make use of it, and it's pretty straightforward. Okay, the harder case is when you don't have an odd power. So what's the program? I'm going to do the harder case, and then I'm going to show you an example of how to integrate square roots and do an application using these ideas from trigonometry. So I want to keep this blackboard. Maybe I'll come back and start here again. So the harder case is when there are only even exponents. I'm still trying to integrate the same form, but now all the exponents are even, so we have to do some game. And here the game is use the half-angle formula, which I've just erased very sadly on the board here. Maybe I'll rewrite them over here so we have them on the board. I think I remember what they were. Okay, so the game is I'm going to use that half-angle formula to start getting rid of those even powers. Half-angle formula written like this exactly it talks about, it rewrites even powers of sines and cosines. So let's see how that works out in an example. How about just the cosine squared for a start? What to do? I can't pull anything out. I could rewrite this as 1 minus sine squared, but then I'd be faced with integrating the sine squared, which is exactly as hard. So instead, let's use this formula here. This is really the same as 1 plus the cosine of 2 theta over 2. And now, this is easy. It's got 2 parts to it. Integrating 1/2 gives me theta over, miraculously, the x turned into a theta. Let's put it back as x. I get x over 2 by integrating 1/2. So notice that something non-trigonometric occurs here when I do these even integrals. X over 2 appears. And then the other one, okay, so this takes a little thought. The integral of the cosine is the sine, or is it minus the sine? Negative sine. Okay. Shall we take a vote? I think it's positive. So you get the sine of 2x, but is that right? Over 2. If I differentiate the sine of 2x, this 2 comes out and would give me an extra 2 here. So there's an extra 2 that I have to put in here when I integrate it. And there's the answer. This is not a substitution. I just played with trig identities here and then did a simple trig integral, getting your help to get the sign right, and thinking about what this 2 is going to do. It produces a 2 in the denominator. But it's not applying any complicated thing. It's just using this identity. All right, let's do another example that's a little bit harder. This time sine squared times cosine squared. Again, no odd powers. I've got to work a little bit harder. And what I'm going to do is apply those identities up there. Now, what I recommend doing in this situation is going over to the side somewhere and do some side work. Because it's all just playing with trig functions. It's not actually doing any integrals for a while. So I guess one way to get rid of the sine squared and the cosine squared is to use those identities, and so let's do that. So the sine is 1 minus the cosine of 2x over 2, and the cosine is 1 plus the cosine of 2x over 2. So I just substitute them in, and now I can multiply that out, and it's not, what I have is a difference times a product. Sorry, difference times a sum. So you know a formula for that. Taking the product of these two things, well, there'll be a 4 in the denominator. And then in the numerator, I get the square of this minus the square of this, right? A minus b times a plus b is a squared minus b squared. So I get that. Well, I'm a little bit happier because at least I don't have 2 different squares. I still have a square. I want to integrate this. I'm still not in the easy case. I got myself back to an easier hard case. Okay? But we do know what to do about this because I just did it up there. And I could play into this formula that we got, but I think it's just as easy to start to continue to calculate here. Use the half-angle formula again for this and continue on your way. So I get a quarter from this bit, and then minus a quarter of the cosine squared of 2x. Okay, now when I plug in 2x in for theta, there in the top ord, I'm going to get a 4x on the right-hand side. So it comes out like that. And I guess I could simplify that a little bit more. This is a quarter. Oh, but then there's a 2. Here, it's half that. So then I can simplify a little more. It's a quarter minus an eighth, which is an eighth. And then I have an eighth of cosine of 4x. Okay, that's my side work. I just did some trig identities over here and rewrote sine squared times cosine squared as something which involves just no powers of trig, just cosine by itself, and a constant. So I can take that and substitute it in here, and now the integration is pretty easy. 1/8 cosine of 4x over 8 dx, which is, okay, the 1/8 is going to give me x over 8. The integral of cosine is plus or minus the sine. The derivative of the sine is plus the cosine. So it's going to be plus the, only there's a minus here. So it's going to be the sine minus the sine of 4x divided by this 8, but then I have an additional factor in the denominator, and what's it going to be? I have to put a 4 there. So we've done that calculation too. So any of these, if you keep doing this kind of process, these two kinds of procedures, you can now integrate any expression that has a power of a sine times a power of a cosine in it by using these ideas. Now let's see. Oh, Leah, let me give you an alternate method for this last one here. I know what I'll do. Let me give an alternate method for doing, really doing the side work over there. I'm trying to deal with sine squared times cosine squared. Well, that's the square. That's the square of the sine of x times the cosine of x. And the sine of x times the cosine of x shows up right here in another trig identity. So we can make use of that too. That reduces the number of factors of sines and cosines by 1, so it's going in the right direction. This is equal to 1/2 sine of 2x squared, right? Sine times cosine is a half, say this right. It's sine of 2x over 2, and then I want to square that. So what I get is the sine squared of 2x over 4. Which is, well, I'm not too happy yet because I still have an even power. Remember, I'm trying to integrate this thing in the end. Even powers are bad. I try to get rid of them by using that formula for the half-angle formula. So I can apply that to the sine of x here again. I get 1/4 of 1 minus the cosine of 4x divided by 2. That's what the half-angle formula says for the sine squared of 2x, and that's exactly the same as the expression that I got up here as well. It's the same expression that I have there. So it's the same expression as I have here. So this is just an alternate way to play this game of using the half-angle formula. Okay, let's do a little application of these things and change the topic a little bit. So here's the problem So this is an application and example of a real trig substitution. So here's the problem I want to look at. Okay, so I have a circle whose radius is A. And I cut out from it a sort of tab here, this tab here. And the height of this thing is B. So that this length is a number B. And what I want to do is compute the area of that little tab. That's the problem. So there's an arc over here, and that's what I want to find. I want to find the area of this for A and B, in terms of A and B. So the area well, I guess one way to compute the area would be to take the integral of y dx. I think you've seen the idea of splitting this up into vertical strips whose height is given by a function y of x, and then you integrate that. That's an interpretation for the integral. The area is given by y dx. But that's a little bit awkward because my formula for y is going to be a little strange. It's constant value of b along here, and then at this point it becomes this arc of the circle. So working this out, I could do it, but it's a little awkward because expressing y as a function of x, the top edge of this shape, it's a little awkward and it takes two different regions to express. So a different way to say it is to say x dy. Maybe that'll work a little bit better, or maybe it won't, but it's worth trying. I could just as well split this region up into horizontal strips whose width is dy and whose length is x. Now I'm thinking of this as a function of y. This is the graph of a function of y. And that's much better because the function of y is, well, it's the square root of a squared minus y squared, isn't it? That's a squared plus x squared plus y squared equals a squared. So that's what x is. And that's what I'm asked to integrate then, the square root of a squared minus y squared dy. And I can even put in limits of integration. Maybe I should do that because this is supposed to be an actual number. I guess I'm integrating it from y equals 0, that's here, to y equals b, dy. So this is what I want to find. This is a formula, an integral formula for the area of that region. And this is a new form. I don't think that you've thought about integrating expressions like this in this class before. So it's a new form, and I want to show you how to do it, how it's related to trigonometry. Well, it's related to trigonometry through that exact picture that we have on the blackboard. After all, this a squared minus y squared is the formula for this arc. And so what I propose is that we try to exploit the connection with the circle and introduce polar coordinates. So here, if I take and measure this angle, then there are various things you can say, like the coordinates of this point here are a cosine theta a. Well, I'm sorry, it's not. That's an angle, but I want to call it theta 0. And in general, you know that the coordinates of this point are a cosine theta a sine theta if the radius is a, and the angle here is theta. So x is a cosine theta, and y is a sine theta, just from looking at the geometry of the circle. So let's make that substitution. Y equals A sine theta. I'm using the picture to suggest that maybe making this substitution is a good thing to do. Let's follow along and see what happens. If that's true, what we're interested in is integrating a squared minus y squared, which is a squared. We're interested in integrating the square root of a squared minus y squared, which is the square root of a squared minus this a squared sine squared theta. And, well, that's equal to a times the cosine of theta, right? That's just sine squared plus cosine squared equals 1 all over again. It's also x. This is x. And this was x. So there are a lot of different ways to think of this. But no matter how you say it, the thing we're trying to integrate, a squared minus y squared, is, under this substitution, it is a cosine of theta. So I'm interested in integrating the square root of a squared minus y squared dy. And I'm going to make this substitution. Y is a times the sine of theta. And so under that substitution, I've decided that the square root of a squared minus y squared is a cosine theta. That's this. What about the dy? Well, I'd better compute the dy. So dy, just differentiating this expression, is a cosine theta d theta. So let's put that in. dy is a cosine theta d theta. Okay, making that trig substitution, y equals a sine theta, has replaced this integral that has a square root in it and no trig functions with an integral that involves no square roots and only trig functions. In fact, it's not too hard to integrate this now because of the work that we've done. The a squared comes out. This is cosine squared theta d theta. And maybe we've done that example already today. I think we have. Maybe we can think it through, but maybe the easiest thing is to look back at notes and see what we got before. That was the first example in the hard case that I did. And what it came out to, I used x instead of theta at the time. Okay. So this is a good step forward. I started with this integral that I really didn't know how to do by any means that we've had so far. And I've replaced it by a trig integral that we do know how to do. And now I've done that trig integral. But we're still not quite done because of the problem of back substituting. I'd like to go back and rewrite this in terms of the original variable y. Or I'd like to go back and rewrite it in terms of the original limits of integration that we had in the original problem. In doing that, it's going to be useful to rewrite this expression and get rid of the sine of 2 theta. After all, the original y was expressed in terms of the sine of theta, not the sine of 2 theta. So let me just do that here. And say that this, in turn, is equal to a squared theta over 2 plus, well, the sine of 2 theta is twice the sine of theta times the cosine of theta. And so when there's a 4 in the denominator, what I'll get is sine of theta, cosine of theta over 2. I did that because I'm getting closer to the original terms that the problem started with, which was sine of theta. Okay. So let me write down the integral that we have now. The square root of a squared minus y squared dy is, so far, what we know is a squared theta over 2 plus sine theta cosine theta over 2 plus c. But I want to go back and rewrite this in terms of the original value, the original variable y. Well, what is theta in terms of y? Let's see. Y in terms of theta was given like this. So what is theta in terms of y? So here the fearsome arc sine rears its head, right? Theta is the angle so that y equals a sine of theta. So that means that theta is the arc sine, or sine inverse, of, well, y divided by a. So that's the first thing that shows up here, arc sine of y over a all over 2. That's this term. Theta is the arc sine of y over a divided by 2. What about the other side here? Well, sine and cosine, we knew what they were in terms of y and in terms of x, if you like. Sine is actually, maybe I'll put the a squared inside here. That makes it a little bit nicer. Plus, and then the other term is a squared sine of theta cosine of theta. So the a times sine of theta is just y. Maybe I'll write this a sine of theta a cosine of theta over 2 plus c. And so I get the same thing. And now here, a sine of theta, that's y. And what's the a times the cosine of theta? It's x, or if you like, it's the square root of a squared minus y squared. And so there I've rewritten everything back in terms of the original variable, y, and there's an answer. So I've done this indefinite integration of a form of this quadratic, this square root of something which is a constant minus y squared. Whenever you see that, the thing to think of is trigonometry. That's going to play into the sine squared plus cosine squared identity, and the way to exploit it is to make the substitution y equals a sine of theta. You could also make a substitution y equals a cosine of theta if you wanted to, and the result would come out to be exactly the same in the end. I'm still not quite done with the original problem that I had, because the original problem asked for a definite integral. So let's just go back and finish that as well. So the area was the integral from 0 to b of this square root. So I just want to evaluate the right-hand side here, the answer that we came up with, this indefinite integral. I want to evaluate it at 0 and at b. Well, let's see. When I evaluate it at b, I get a squared times the arc sine of b over a over 2 plus y, which is b, times the square root of a squared minus b squared, putting y equal to b, divided by 2. So I've plugged in y equals b into that formula. This is what I get. Then when I plug in y equals 0, well, the sine of 0 is 0, so the arc sine of 0 is 0. So this term goes away. And when y is equal to 0, this term is 0 also, and so I don't get any subtracted terms at all. So there's an expression for this. Notice that this arc sine of b over a, that's exactly this angle. The arc sine of b over a, it's the angle that you get when y equals b. So this theta is the arc sine of B over A. Put this over here. That is theta 0. That is the angle that the corner makes. So I could rewrite this as A squared theta 0 divided by 2 plus B times the square root of A squared minus B squared over 2. Let's just think about this for a minute. I have these two terms in the sum. Is that reasonable? The first term is A squared, that's the radius squared, times this angle times a half. Well, I think that is exactly the area of this sector. A squared theta over 2 is the formula for the area of the sector. And this one, this is the vertical elevation. This is the horizontal. A squared minus B squared is this distance, square root of A squared minus B squared. So the right-hand term is B times the square root of A squared minus B squared divided by 2. That's the area of that triangle. So using a little bit of geometry gives you the same answer as all of this elaborate calculus. Maybe that's enough cause for celebration for us to quit for today.